Okay, I'm going to try and finish up the homework here. I am going to skip a couple because we haven't gotten to those yet. We'll get to them after spring break. So, all right, this one is supposed to have a diagram. I don't know where it went because I thought it was in, hopefully you see it in your homework. Maybe it just didn't print. I don't know. But with this one, we've got 4 particles, and I made one of these in class. Like I showed y'all this in class. This was actually on another one of our problem sheets. So this is my axis of rotation. And I've got these 4 identical particles. They all have a mass of m, and they're all connected. And they're all like the same. All of these little lengths are the same. And they can rotate around. So imagine like taking this and whirling it. I didn't bring my demo item home, so I can't show it, but whirling it, and then this whole thing is rotating around this axis. Why would you have that? I have no idea. But anyway. So what's the rotational inertia of this array of particles? And sometimes, I believe on the mock exam that we enjoyed Saturday, there was a similar type problem to this where there was an array of different particles or particles in different placements. So this could come up. All right, so these are all going to be point masses. Okay, so we're going to use m times r squared for each. Mass is the same, but their radius is going to be different depending on where they're at. Okay, so let's call these particle 1, 2, 3, and 4, because that's the way I had labeled them for whatever reason. So for particle 1 has a radius of 0 because he's actually on this axis of rotation. So he's going to have a mass of 6, but then his radius is 0. So he's actually not contributing anything to our overall rotational inertia. Particle 2 has a mass of 6, and then he is, let's see, so we have to do we have to do Pythagorean theorem here? Not really, because, I mean, these are all 6, so this is also going to be 6. So 6 squared, basically that's 6 cubed, I guess, 216. Particle 3, okay, is going to be the same as 2 because he's in the same placement, just instead of here, he's here. So, and then 4, okay, 4 is 6 plus 6 from the axis of rotation. So 4 is going to be 6 mass times 12 squared. Okay, so that's 6 times 12 squared is 864. So if I add up 216 plus 216 plus 864, I get 1296, and that's pretty close to 1300. So we added all these point masses up based on their placements. All their mass was the same, but then their placements were different relative to the axis of rotation. We note that 1 doesn't contribute at all, okay, and then 2 of them have the same rotational inertia, and then 1 of them has much greater because he's a lot farther from the axis of rotation. So, all right, so we've got a merry-go-round on a playground. I don't know how to draw a merry-go-round very well. And so we're going to say it's a disk with this equation for rotational inertia. We're given a mass, we're given a radius, we're given an initial angular velocity, and it comes to a stop or comes to rest, so that means our final is 0, and we're given a time. what's the net torque due to friction. So basically it's spinning and it's going to come to a stop because of friction. All right, so this is one where we can combine a couple of things. We want net torque. So we'd like to use that equation. We need both of these things. Okay, so we can get the rotational inertia is 1/2 mr squared. They give us the mass as 200 kilograms and the radius is 12 meters. So I'm going to use 1/2 times 200 times 12 squared. Gives me basically 100 times 12 squared. 14,400 for my rotational inertia. It's a pretty big mass and radius, so okay. So we've got that value. We need this. How could we get that? We've got a few kinematic variables here. So I'm going to remind myself that I've got this little handy equation. And I can use that to solve for angular acceleration. Put in values, comes to a stop, so final is 0, equals 4 plus 16 times alpha. I'm going to get alpha is remember that's my angular acceleration is minus 0.25 radians per second, because it's slowing down. This merry-go-round is slowing down, coming to a stop. So now I can take this times this, and that's going to give me my net torque. And that is 14,400 times minus 0.25 equals 3,600. And there's a minus there. That's going to tell me what direction my net torque is in. So I must be moving clockwise because I'm slowing down. I have a minus sign there. But my answer is 3,600 newtons per meter. And it said magnitude, actually. It didn't say anything about direction, so never mind that. Magnitude due to friction is 3,600 newtons per meter. So, okay, let's see. I think I can get to the last question. I'm going to skip 11, 12, and 13 because they all have to do with angular momentum. We're not getting to that till after spring break, so you'll see those again later. The last question has to do with rotational energy, which we're going to talk about tomorrow. So I'll just go ahead and spoiler that for a rolling object, okay, it has a kinetic energy, rotational kinetic energy of 1/2 times I times omega squared. Okay, this is analogous to the kinetic energy you've already seen. Oops, you can't see that. 1/2 mv squared. Remember, m is analogous to I, rotational inertia. Here's my linear velocity. Here's my angular velocity. Okay. So if we want our kinetic energy of this cylinder, let's see what we know about this cylinder. Cylinder rotates with a constant angular acceleration about a fixed axis. I value is given as 6 kilograms times meter squared. At time t0, the cylinder's at rest. At 2 seconds, its angular velocity is 4 radians per second. What's his kinetic energy at that time? So there's a lot of stuff given here, but in the end, we're really just going to use this equation to get the kinetic energy. 1/2 times 6 is our rotational inertia, times 4 squared is our angular velocity. If I do that, let's see, 1/2 times 6 is 3, times 4 squared gives me 48. See if that's a choice. 48 joules. So we'll talk about kinetic energy tomorrow for rotating objects. That's kind of most of what we'll talk about. That's the equation. And then we can do a bit of conservation of energy, which we'll look at tomorrow. So, okay. So that's all those homework problems.